All right, guys, DNS exam 4, problem number 36. These ones are tough problems, and I don't know how likely you are to actually see one like this on the real AP test, but it shows up enough in the review materials that it seems like we maybe want to go over it. Actually, let me amend that statement. Given that you guys aren't taking any multiple choice questions this year, I think you're very unlikely to see a problem like this. But hey, maybe we can learn something by going through it. So what we have is a limit expression right here. A limit as n approaches infinity times the quantity 1 over n times, and here we go, 1 over n squared plus 2 over n squared plus 3 over n squared, 4 over n squared, yada, 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 until we get to right here to the n minus 1 over n quantity squared. And they're telling us that that expression right there, for if n is a positive integer, can be expressed as one of the following integrals underneath there. So the important thing to take here, of course this had to be an integral. We're talking about a limit here as n is approaching infinity, and it's then the sum of this big expression right over here. Well, that's exactly what we do when we set up definite integrals and what we did back at the beginning of chapter 5. Now, the first thing I want to talk about right here is determining what exactly n stands for and using that then to determine our limits of integration. Okay, so the first thing to remember is in all of these problems right here, n always represents the total number of rectangles that we're dividing our interval into. Okay, the total number of rectangles that we are dealing with right there. So they tell us that n is a positive integer, so it's not a bad idea to think about n being a relatively small value early on, like 2 or 3 or 5, but with the understanding that the number of rectangles is going on to infinity. The first thing we want to recall is that this expression that's going to get pulled out in front there is going to be the common width of each one of our intervals right there. Okay, the delta x is what we have right there. And that formula for delta x that we used back in the day was b minus a divided by n. Well, they tell us in this problem that that width of each rectangle is 1 over n. Now you'll notice here the denominators are both n. That tells us then that the difference of b minus a has to equal 1. B being the right endpoint of your interval, a being the left endpoint. So that tells us right now that d is not the correct answer to this one, because your a and your b value here in part D are 0 and 2, so b minus a would be 2 instead of 1. But also, though, guys, just as a general test-taking strategy, if you notice that 3 of the choices have the same limits of integration and a 4th one does not, it's pretty unlikely that that odd man out right there would be the correct answer. So this kind of narrows it down to either A or B or C. Now as we look at these 3, there's a couple of different ways of looking at it right here. But what I thought was maybe the most helpful was this. If you take a look at both A and C, both of those are functions that are hyperbolas, where, let me draw just a quick sketch of what's going on right here. The graph of 1 over x squared, and again, everything is to the right of the x-axis here, so I don't really care what's going on the left. In both 1 over x squared and 2 over x squared, those graphs essentially look something like this. And what that means is that if you were now going to take a region right here and cut it up into a whole bunch of rectangles, and I don't really care whether we're dealing with left rectangles, right rectangles, it doesn't really matter right now, you can see that for both 1 over x squared and 2 over x squared, the heights of those rectangles are decreasing as we move from right to left. Now, contrast that with the graph of, let me switch to purple right here, with the graph of the function x squared, which is a parabola here. I guess I did that. Yeah, here we go. All right, to the graph of x squared, which is a parabola opening upward. And now if I try to draw rectangles underneath that, now what we're going to see is that the heights of those rectangles are increasing as we move from left to right. Now that becomes important because if we take a look at these terms inside the brackets right here, if we recall, the 1 over n out in front represented the width of each one of those rectangles, but what's left inside the brackets represents the heights of all of your rectangles. So I found it informative right here to simply think about, okay, for a particular value of n, just knowing that n had to be a positive integer that was eventually approaching infinity, but for a particular value of n, if we look at this y value right here and then compare it to this y value right here, did it get bigger or did it get smaller? Well, in looking at these two fractions, since the denominator stayed the same and the numerator increased, that means that this second height is actually greater than the first height. And likewise, the 3 over n would be even higher than that. And eventually, the n minus 1 is going to be very close to that n value right there. That's going to be even higher. So every time we move from left to right, the heights of our rectangles got bigger each time. In both A and C, your heights are getting lower as you move from left to right. So that means then, guys, that given everything we've considered right here, the only possible answer to this question now of something with an overall width here of 1, which excluded D, and something whose Y values were increasing as we went from left to right, that excluded A and C, the only possible answer to this one here, everybody, is B.